You are not audible.
Hello, sir. Sir, I think you are on mute. You're not audible.
So, can you hear?
Sir, we
Yes,
can
sir.
hear you now. I'm sorry, from the beginning,
Uh,
there was no audio from your end. We thought you were testing the slides.
okay, shall I start again?
Yes, sir, please. If you could, thank you.
Okay, okay. I will. Okay, today the lab session regarding that MATLAB interfacing with C2000 microcontroller, and this is the overview of my presentation. Basically, the introduction of that microcontroller, and corresponding we are choosing the best microcontroller regarding that our powertrains based applications. That was TMS 320F28379D microcontroller. After that, we will show some launchpad pin overview and description of each and every pin uh, available in that microcontroller, and corresponding we will discuss some important modules. Important modules is available in that microcontroller. Those are general purpose input output module, and extended pulse width modulation module, and corresponding ADC and DAC module. After that, we will show some introduction to CCS Studio for program development environmental. And coming to the C2000 real-time microcontroller overview, this real-time microcontroller platform is designed for high efficiency getting in power trans applications basically, such as high power density and high switching frequencies like GAN and SiC technologies. And the main capable of this C2000 real-time MCU has sensing, control, and process, and interface only. Then in case of sensing, if you see the sensing, they are provide a highly accurate sensing. Those are 12-bit based and 16-bit based, and total 24 channels are they are provided, the Texas instrumentation. And externally they were giving that to DAC axis also, and corresponding that some quadrature encoder and capture logic sensing module also they are provided. Then coming to that, in case of control, they are provide highly flexible and high resolution PWMs are available. Those are up to 32 outputs, and these outputs are tightly coupled with science domain for fast response time, and also give some buffered output DACs also. Then coming to that process of that C2000, they are used highly performance processors. Those are floating point DSP C28X core plus parallel multi-core architecture it has. And at a time in this processor, that instruction was 925 MIPS will be flow on in that microcontroller. And coming to interface, if you want to communicate to system to microcontroller, we need some interface is required. Those interfaces are they provided like CAN FD, LIN, UART, SPI, I2C, and USB and Ethernet MAC and CAT and XEMFs. And these are the main microcontrollers are developed by that Texas instrumentation based on that performance only. Here, our require and present trends based on power trends application oriented. Here we are choosing that TMS 320F2837XD microcontroller. So we are showing regarding that microcontroller overview only here. Coming to based on that microcontroller, these are the features are available. That first feature is it is dual core architecture. It has basically, and the core frequency. The clock frequency is 200 megahertz. Means it's take to execute one instruction is take only 5 nanoseconds only. And coming here they are using 32-bit processor, and it has both floating point multiplier unit and a fixed point multiplier unit also available. And externally they are providing trigonometric math unit and complex math unit. Means here that complex math units are reduce the computing time for complex math operations only. And externally they are provide the two programmable controller accelerator. The accelerators are used to execute code independently of main CPU only. And that microcontroller has on-chip memories are two. Those are flash memory and RAM memory. The flash memory was 1 MB nearly, and RAM memory was 204 KB only. Coming to some system peripherals corresponding that F28379D microcontroller, uh, it has two external memory interfaces and dual 6-channel direct memory access controllers, and up to 169 individual programmable and multiplexed general purpose input or output pins are also available. And in this microcontroller has two CPUs. Each CPU has 14 peripheral interrupt lines are has, and out of 14, two interrupts 13 means interrupt 13 and interrupt 14 are directly connected to CPU timers 1 and 2. Means each CPU has two timers again, and the remaining 12 peripherals means peripheral interrupts will be connected to uh, enhanced peripherals only. Those we call EPIS. Then coming to communication peripherals, in this communication peripherals are USB for debugging purpose we are used. Here they are provided isolated XDS 100V2 debug probe they are giving, and after that in that microcontroller internally two control area networks modules are also available corresponding SPI ports and SCI, means serial communication interfaces, and multi-channel buffer serial ports also available. And externally they will give two I2C, means integrated control interface also they will provide, means in that controller provided. Coming to sensing, means analog subsystem. In this analog almost up to 4 A to D, means analog to digital converters are utilized in this, and almost 24 ADC outputs are available, means ADC pins are available. In that 24, some pins are 16-bit mode differential inputs based are available. Some are available in 12-bit single-ended inputs based are available. And also they will give three 12-bit buffer DAC pins, means peripheral also they will provide. Then coming to that enhanced control peripherals. In these enhanced control peripherals, the most one is that control peripheral, that was EPWM. In these 24 channels are available in that microcontroller, and after 24 for pulse width modulation only, after that 16 high resolution pulse width modulator also they will provide, and 6 enhanced capture modules also available. These are used where accurate timing of external events are required. There only we can use that ECAP peripheral. And coming to enhanced capture encoder pulse modules. These are used to get the information of position, direction, and speed of the rotating machines, where we want to position control systems are utilized. There only we can access these EQP peripherals. And this is the top view of that TMS 320F 28379D launchpad. If you see that J1, J3, J5, J7, those are the jumpers, means we can access from that jumper points only. Means here that J3 and J7 jumpers are provide ADC accessing, and J1 and J5 are accessing that GP IO accessing only. Means we can utilize it for any digital in or out. And coming to J2, J4 and J6, J8, here the J4 and J6 are enhanced PWM channels are available, means we can access directly from that pins from J4 and J8. And corresponding J2 and J6 also, again that GPIOs and some serial communication, means communication purpose also we can utilize those pins. And coming to that J14 and J15, we can accessing that encoder, means for sensing that speed of any motor or position of the motor, anything we can accessing by using that J14 and J15. At that time we can utilize for two motors. And J12, J13, J11, these are the communication purpose we can utilize those pins directly accessing. If you see that left side of the system, means figure that exceeds 100 V2, that was probe connection, we can give into there only. Here the JP1 and JP2, JP3, they are the jumper points. If you remove that, means disable that jumper points, and it will be isolated from that circuit to system. Okay, so we can externally we can use it for anywhere. Means offline system also we can utilize that one. Means it has flash memory. So by using that flash memory we can utilize anywhere. And this is a launchpad ka pin overview. If you see that right side of that one, that J4 and J8 corresponding, that PWM accessing. If you see that GPI pins and EPWM pins are they are mentioned there. They are mentioned. This is the J4 and J8 pins configuration, and this is the J2 and J2 and J6. And if you see the left side of launchpad, these are the ADC accessing points, and also here some GPI accessing and some communication purpose SPI and I2C. Like if you see that pin configuration, we can utilize it as a GPI and some communication purpose, and a sensing purpose also we can utilize it from left side. For right side, we can utilize it as a controlling purpose. And this is that same figure, but in terms of letters we are showing here that J3 and J2 and J1 and J4 corresponding. If you see that pin number corresponding that what is the action or done with that pin here. If you see that one, so we can see that pin number, then directly we can accessing corresponding the GPI pins. For this is for J5, J7 and J6, J8 and J6 ka pin overview actually. And coming to the main on-chip modules of that microcontroller, that F28379D ka, here we are explain regarding GPI module and EPW module and inbuilt ADC and DAC only. If the time will exist, we will cover that remaining EQP module and timer module and communication peripherals also. Coming to GPI module, basically in that microcontroller has basically we can utilize that GPI pins is an uncommitted digital signal pin in the that MCU. It may be used as a digital input or digital output. It can be used. In this microcontroller has 169 GPI pins are available. These pins are grouped as a 6 ports basically, and each port has 16 pins access to. Means if you want to access that GPI through multiplexer only, we can accessing the GPI pins only. So here each port has 16 pins. So each port has 32 pins. Out of 32, 16 pins will accessing through MUX 1 only. The remaining 16 pins you accessing through MUX 2 only. If you see that ports A to E, each port has 32 pins only. The remaining 9 will be corresponding port F only. if you want to accessing GPI pins, it has two registers are required. Those registers are direction register and data register only. If that that direction register will specify the direction of GPIO pin. Like if you give 0, it has configured as a input. If you give 1, that was configured as a output. That was give the direction if you want to utilize it as a input or output. The coming to that data register, it indicates the current status of the GPI pin. Means for what purpose you have to use that one. And after that some registers also there for if you want to clear that GPI pins using that GPI clear, and if you want to set that GPI set and toggle that GPIO using that GPI toggle. These commands we are used in while if you doing programming in microcontroller only, we can use that this terminology. But now through MATLAB accessing through means model based accessing, it cannot show those options directly. We can directly choose that pin number corresponding for what purpose we have to use it to that GPI only we can see in model. From onwards, my colleague was continued to the MATLAB interfacing with each and every modules from here onwards. Thank you. Yes, though both bipolar and unipolar. But but no, ma'am. For both, we can utilize it for that ADC. But that microcontroller will taking as a with only positive. Means we can provide some offset also we can provide. Then only we can giving to microcontroller. Otherwise, if you give that bipolar also, then that microcontroller will be damaged. Uh, Um, if we can, yeah, if you can provide offset or signal conditioning something, then we can utilize any means. For both condition, we can utilize. Means we can up to 0 to 3.3 volt only we can do that thing. Thank you.
Hello, am I audible? Um, Before going to access the peripherals of the C2M microcontroller, first let's see uh, how to install the C2M microcontroller block set in the MATLAB, and then how to interface the C2M microcontroller with a particular file in the Simulink file, and then we will see the how to access the peripherals like ADC, DAC, GPIOs, EPWMs. So we're going to now MATLAB file. So we'll open a Simulink file and we'll create a new model. So first of all, we need to install this C to the microcontroller block set. So for that, we have to go to modeling and we will open the model settings and we will go to hardware implementation and hardware board. We should go to get hardware support packages. And we have to search here C2000 and this block set must be installed in your MATLAB. So then we will be installing this microcontroller block set, and we can able to see whether block set have been installed or not in the library browser. See, we have installed a Ceto microcontroller block set. Here we can see that we have multiple block sets, multiple microcontrollers have been installed with their library files. And here in this session, we are going to use only 3MS 320F 28379 microcontroller. This is the one. You can see we have library file. You can see we have installed all of library files of different peripherals, ADCs. We can see here DAC, EPWM, GPIO pins, and other communication protocols like SPI, I2C, and all. Now we have to interface our MATLAB file with our microcontroller. So let's see how to interface the microcontroller. Again, we have to go to my modeling. We have to select the particular board which we are going to use. See here we can have two different boards. We can see here two different boards, F27990 and Launchpad. This 28379 XD will be in experiment kit, that is different board, and here we are using Launchpad. So we have to select the Launchpad. So it will inside the hardware parameters, and we get the hardware parameter values. And we can see here all the options which have been installed. Different peripherals we can see here. I'm not changing any settings, which are default settings made by MATLAB file. And now going to solver. It will be by default will be fixed step, and automatic solver settings. I am using here OD3. We can use any solver settings, but I prefer OD3. And here I'm setting the fixed step size 5e power 05, which is sampling frequency will be 20 kilohertz. And now how to set up? We need to set up our hardware board. We have installed only library block set, but we didn't set up the microcontroller to our this particular file. So we need to set up our hardware. So we'll get different microcontroller things here. So we have to select a particular which we are going to use. So we are using here Delphino family 2837990. So we have to select it. This is the third-party software which you have to install. And additional to MATLAB, we should have this control suite, Code Composer Studio, and Ctronware. And the version must be this, whatever version they have mentioned, or lower versions. Upper versions will not be installed because the MATLAB 2023 have been upgraded, has been installed with this particular version only. Next, we have to validate the CCS folder. That, we are ensuring that all the processes which I have selected are supported or not. And next, Ctronware, we have to validate it. And this is a summary. And we have selected 3790 with this particular file. So whatever you do in this file will be generated in the code, and that will be dumped to your microcontroller. So now let's start accessing the GPIO pins. So we need GPIO will be general purpose input and output. Here we are using GPIO as an output. So we should use a digital output. So to see the output of the digital GPIO output, we are using a pulse generator, and we are generating the pulses with a frequency of 2 kilohertz, sorry, and 50% modulation. We have selected GPIO, but we didn't select which GPIO pin we are going to access it. So we have to open this block, and we have to select which GPIO pin you require. So there are multiple GPIO pins we can as explained by my previous colleague, that there are 169 GPIO pins. So we can have all the access of GPIO pins you can see here, and I'm using now GPIO 0 only, which pin number 40. And I'm now, see here we have during build and deploy, we have two options. One is build option and one is build and deploy and start. So first of all, we build a model that doesn't require any microcontroller connected to our system to ensure all the parameters have been installed properly or not. You can see here the diagnosis, and it has been showing that it has been processed complete successfully. That means all the things have been right. Now we are going to build and deploy it in our microcontroller which we have connected it. Relevance deploy किया नहीं. No, check it out. Generator 40 pin. 40. Pin number 40. You can see the output in here. Pin number 40. And the output of this program will be Chinna. It is less actually. Uh, you can see in the video, you can see observe that there is 50% duty cycle with 2 kilohertz frequency has been running in the program. We have kept 2 kilohertz frequency and 50% duty cycle, and this is complete frequency 2 kilohertz, and this is 50% modulation, and you can see in the video. Two standard ones. Now let's generate the PWM with not with pulse generator. We can generate the pulse generator using I'm giving you 50% duty cycle, and I'm selecting the frequency as 2 kilohertz. I am now build and deploying the code. Run over. Hello. Build and deploy has been done, and you can observe in the camera the pulse width modulation. When you generate the SATU generator in the MATLAB file, you're getting this MATLAB in the code composer. MATLAB SATU generation will be in such a way. So it will not be pure triangle. It will be having some samples. It will be generating sample time, and it will be increasing in counter wise. So when you use in high frequencies, the resolution will be decreased a lot. So to overcome this, enhanced pulse width modulation pins have been introduced, and due to this, without the use of sampling time of the model, we can select our frequencies and based on the system clock frequencies. So in EPWM, how to set the EPWM in EPWM, how to select these uh, generate the sawtooth or triangle pulse generator using the clock system clock frequencies. So PWM will be representing an analog signal with a digital approximation. You can see here it is having a constant pulse amplitude with it is consisting of constant amplitude with variable pulse widths. And here in this board we are having only six PWM channels, which is having only 12 PWM outputs. And each PWM output will be having the channel will be having EPWM A and B, and it is having a 16-bit time-based counter, and EPWM module consists of eight submodules. It is in 8 submodules. In time-based counter, we're going to define the TB clock or clock frequency of the controller, and then we are going to define the period, how much time it has to count and set back to 0 again. And then we are having the compare registers where our modulation index will be stored. As I said, it has been A and B. One compare registers will be present. One will be storing A and one will be storing B. And next, in action qualifier, when modulation index meets intersects our triangle or sawtooth, what actions must be taken? It should be set or clear or should do nothing. That actions can be defined in this action qualifier. And next, there will be one deadband generator module. This is another advantage of using the CPW module. In deadband, we are going to give certain deadband between in inverter. When it comes in the H-bridge inverter, one leg consists of 2 switches. it will have deadband between two complementary pulses, because due to in practical scenario, the the pulse uh, the pulse generation output of driver and the switch will have some delay to turn it on and turn it off. So in order to avoid that short circuit, so these two will be having two complementary signals, and whenever it turn on, it will be turned off. So due to delay in the driver output and the switches, they may be not be simultaneously turn on and turn off. So there will be some delay. To overcome this short, when the switch, this is turned on and this will be not turned off completely, and there will be short circuit. So to avoid such conditions, we should give a deadband to our complementary signals. So this deadband will be giving that delay in the complementary signals. And we have freedom chopper, trip zone, compare, and event trigger. In event trigger, again we are going to trigger we are going to have ADC channels and all different events in the model in the system. So after sampling, after switching frequency done, it has to trigger another event. So that can be done using this event trigger option. So as I shown previously, that sawtooth triangle pulses will be in counterwise type. So this one gap, the time gap between these two count up from 0 to 1, this will be called as TB clock, and how much time, how many counts will be done, that will be counted as counter, or we can call it as TBPRT period. How many counters it will be done? So here see at one clock cycle, it will be one clock cycle will be rising one count up, and the one again at rising clock will be having one more count. Similar like this, we are going to count that this value of the counter we are going to define, and this clock frequency we are going to TB clock will be defined, and according to that we are going to define TWPM. PWM frequency can be calculated from this formula. Then how this why this one has come? We are starting from 0 here, not from 1. So in order to add this 0 term also, we are going to add this 1. So let's assume now I'm taking as TB clock as some 10 power 8, and TB PRD we have to calculate, and I know the frequency will be some 10 kilohertz frequency. So here will be 10 kilohertz into TBPRT, and this will be gone to 10 power 8. So it will be 10 power 4 will be our TBPRT plus 1. So TBPRT will be 999, say 4 nines. Similarly, this is up counter. Similarly, the same thing will be counted to down counter. This is the down counter, and this is the up counter. So both will be having same formula, and from this we found the TBPRD count should be 449. So this count will be from 0 to 49, with a TB clock will be 10 power minus 8 seconds. Now coming to here, now coming to triangle. Before it was sawtooth, now it's coming to triangle here. Here triangle will be, one side will be up, and the side will be down. So it will be like 2 times. So 2 times of TBPRT into clock. So what happened to this one? Actually, we are counting this as twice. So that one will be eliminated. Now how to define? So we will going to give this TBPRD value and we'll calculate we are TBPWM and TB clock. So this TBPRD we are going to calculate from the formula. But how to define this TB clock? Whatever value we have to give this TB clock. So TB clock can be defined from system clock frequency. So system clock. So this is the calculation for TB clock. So initially the EPWM we have to calculate EPWM clock. That will be by default system clock by 2. Our system clock frequency is 200 megahertz. That will be our microcontroller clock frequency. By 2 will be 100 megahertz. And from this TB clock will be calculated. So here we can define our TB clock by having different values. So initially by default it will be 1 by 1, or else I want to reduce my TB clock. That can be defined. That can be defined by this values, or in programming can be by these values, or else in the MATLAB I will show you how to give these values. It can be 2, HSP clock will be 2, and it can be 1, or it can be 1 by 2, or it can be 2 by 2, depending upon what value you require. That can be this TB clock can be calculated by we can manage the TB clock value by varying the values of HSP clock and clock division. So let's see how to give these TBPRT values, and then we'll come to this axiom qualifier. So we are going to get EPWM block from here to here. So this is the TBPRT value. And here we can see here, this is the what I'm saying about HSP clock and clock divisions. This is the clock division. This is the HSP clock division which you have to give here. You can see here we have different types of different numbers 1, 2, 4, 8, 16. So we can define the value of 1, 2, 4 of clock division. And here also in the pre-scalar divider we can see here this also can be given in terms of these values. So here we can define what value you want according to TB clock. Now I am keeping the just same default values here, and I am defining the TB PRT value based on. So what I have my aim is to generate 10 kilohertz sawtooth triangle. So as per formula, TPWM equal to TBPRT plus 1 into TB clock. So TB clock, we have to define EPWM clock will be by default will be 100 megahertz for this 28370 microcontroller, and HSP clock I have kept 1 and 1, so it will be 10 power minus 8. So we have defined the TB clock now. Now how to get the TB PRD value? So from this formula we are going to get it. So I set as PWM frequency as 10 kilohertz. So TB PWM will be 1 by 10,000 equal to TB PRT unknown. We'll keep it at this. And TB clock we have known from here. It is 10 power minus 8. So TB PRT plus 1 equal to 10 power 4. So TBPRD equal to 999. Say 4 nines. So we have to give this value here. We have to give this value in this timer period value. That 4 nines value will be given here. And here we can see that the counting mode up, down, up, down. So I said sawtooth triangle. It can be up or down. So I'm choosing here up counter. I have defined these two. Now we have to now come to this is EPWMA where action qualifier. The actions can be 4 types. One action will be at one counter is equal to 0, and another action will be when counter is equal to period. So another action will be when counter is equal to modulation A index. As I said, EPWM consists of two channels, EPWM A and B. So here we are using EPWM A. So when modulation index A happens, what should be the action? Here in counter B, what should be the action? That will be known in the graph. So this is the action qualifier. Here we have, so you can see here, see this is our sawtooth generator, and this is a compare A modulus index and A and B modulus index, and this is the period which is equal to 499, and this is our 0. So when at 0 point, what I'm saying, when modulus index equal to 0, then when this has been 0, I think that it is set. So it should be 1. I'm keeping it as set. And when it is equal to period, I will talk to later when I come there. So now at compare B value, I'm not doing any action. So it will be do nothing. And when TBPRT when compare A action meet the triangle, it should be clear. So it has been cleared here. Again, when 0 has come, and this point has 2 points. One is period and one is 0. As we already defined at 0, it should be set. So we will do no action at period. So we will giving at period, there will be nothing, no action or do nothing. This is for only A module. Now we can see here in the B module what happens when it crosses 0. I'm setting it up. So it will be set. And period do nothing. And when compare B has been there, it has to set down. So this is at A. So this is the action where it has crossing the A modulus index, and this is B modulus index. So when it met at modulus index B, here it do nothing. But in EPWM B, I'm setting it as clear. So here we can get two different modulus index in EPWM module A. This can be some 60% and this can be some 30%. So we can get two different modulus index in the EPWM channel A. So here what I said in EPWM A, there will be only and when it counter is equal to set 0, it will be set. And when period, I said do nothing. And when counter is equal to compare A, it will be clearing. And compare B, it will be do nothing. Now coming to B channel, I'm enabling it. Now we can see here. Here when counter is equal to 0, it should be set. And when period, do nothing. And when compared is equal to A, it should be do nothing. But when compared to B, it should be clear. So now how to give this two different modulus index in the EPWM block. See, we have here compare A modulus index, B modulus index. We have C and D. But in 2837ND, we have only A and B registers. This is the block which have given for multiple block sets. Not only this, what to say. You can see here we have different block sets. 2837ND and 07X and 044X also. So in 2837ND we have only A and B, so we have to utilize only A and B. We should not do anything to the C and D. So we are opening now. So we are giving here setting up modulus index. So here I am giving, I want to, you can define inside the block or outside the block. In inside block, we can give the value of the compared value inside, but I want to give it outside only. So we can use input port, you get the output block. Here you have the output block of A. Similarly, when you have, we want to get the block of output of B also. So we have to define B. So I'm giving it modulus index of 5. As you can see here, only 0.6, and you can connect it here. If you connect directly here like this, then you are not going to get any output because the value will be compared A value will be only 0.3. So, but our TBPRD value is 10,000. Here value is 0.3. So, in order to get the proper compared value, we have to add a gain here with TBPRD value. So we still had here TBPRD value. Then we are going to get the output of pulses. Hello. EPWA will be, here we were using EPW1. 1A will be 40 and 1B will be 39. And similarly, when you go for 2A, 2B, then it will be sequentially 40, 39, 38, 37. So output you can see in the camera, and I'm here displaying the output also. Gain value will be TBPRT value only. Whatever value you have given for TBPRT. So I will explain you it. 9999. 99. So this will be the outputs of EPWM-A and EPWM-1A and 1B, which you can see here. Now let's see how to give the deadband value. So I'm giving only EPWM-A now. I'm disabling the EPWM-B, and I'm not enabling in any EPWM-B, but when you enable the deadband unit, the EPWM-B automatically you can see the output. So here we have different deadband polarities: active high, active low, complementary, active high, complementary, active low, complementary. So depend upon your application, you're going to use this deadband polarities. So I will show the how these deadband polarities have been decided. So you can see here, deadband polarities will be see, this is the active high complementary, active low complementary, active high, active low. Suppose I have inverter which is having which require two complementary pulses for across switch. So when this is turned on, it will be turned on. So let's see in active high complementary. Here see when there is a turn, when the pulse is turned on, this is completely turned off. This is one. This will be having a complementary to this. This actually it should be like complementary will be like this. But as we given deadband with active high complementary, this will be the our deadband timing which we have given it. So this deadband value will be coming here, that this active high will be complementary, this active high will be reduced rather than decreasing in complement in lower signal. This will be, this bandwidth will having the lower value. So in case of active low complementary, you can see here, this will be having higher bandwidth compared to this one. So what happens here, when in this case, this is turned on, one, and this is also turned on. So what happens, this short circuit. So in this case, we should not use active low complementary. And in case of higher, here also we have 1 and 1. or here in this case of low complementary, we have 0 and 0. So based on your application, you are going to decide which you have to decide. So in my case, it is an inverter. So we are going to use this active high complementary. So here I am using active high complementary, and I am keeping signal source for both EPWM and I am giving here value of 100. Here 100 value means 100 value will be equal to 1 microsecond. 100 will be equal to 1 microsecond. If it is 200, it will be 2 microsecond. It will be multiples of 100. So I'm giving it here 100. And I'm using the shadow registers immediate because using shadow only. So I'm deploying it. So that band once. You can see in the camera there is a dead band. 100. So you can have the dead band having 1 microsecond. So I can show in the graph. See here we have given 1 microsecond and this block consists of 5 microsecond and this is having this gap, it belongs to comes under 1 microsecond here and this will be 1 microsecond. And regarding phase shift of giving in the PWM pulses, that will be handled by my colleague Ritwik.
So basically, I will be handling the phase shift of that PWMs. So we can do phase shifting through two methods. One is that master-slave synchronizations, and other is that phase shifting by compare A and compare B values. So firstly, we will see this synchronization method. So in PWM block, in this ePWM block, we will see this option that synchronization action. So we have to first select that which one is master and which one is slave. So if we select ePWM as master, so we have to disable this synchronization action here so that we can provide that uh, which one is master select. So here EPWM is master, so we have to enable this mode, synchronization action. And in that slave part, EPWM2, we have to give that uh, means how much phase delay we have to provide. So that phase delay we can calculate from this formula. And if we are using up or down counter, then this will be the formula. And if we are using that only up down counter, then this will be the formula. So let's say we have to give 36-degree delay means phase shift. So we have to calculate this using this formula, using this one, because we are using this up counter only. So this through this formula, this TBPRD is uh, so this thing is phase shift we have to calculate from this phase shift is 36-degree. So 36 will be here, and this will be calculated from that formula that sir have told you, that 200 by 2. So this will be approximately 100 megahertz. So, sorry, this will be 100 only. So from here we can calculate this one, 100 into 36 by. So this will come from this time period, means this thing is the time period of that pulse we have given. So this time period will be generated here according to that the frequency of that PWM pulse. So here we have selected frequency as 20 kilohertz. So 20 kilohertz will come by this formula, that the E- the TBPRT TB TBPRT will be equals to that system frequency that is 100 megahertz by that the required frequency. Required frequency is 20 kilohertz. So TBPRT will come from this formula. It will come by 500 5,000. So this is this one. This TBPRT. So TBPRD. So from here we will put this TBPRT here, 5,000 into that phase shift. This 36, if we require 36-degree phase shift, 36 by that 360. So it will come 500. So here we have to put this value. This TBPH means phase shift value. So after this phase shift will come. Simulation. And here you can see that we have to select that which PWM we are selecting as masters. So here EPWM1 is master, so we have to provide that link. From MATLAB. New model. New model. New model. delete. So in this block, as you can see, here is this option, means synchronization output. So we have to enable this one. So by enabling, we provided that this EPWM1 is our master. Next, we have to select other EPWM block. So here this EPWM2 is our slave. So we have to provide this synchronization action, means set via dialog, or we can set here only. So here we have to provide this value, means how much phase shifting we require. So that phase shifting we have calculated from that formula. So if we required, means 10%, so we have to calculate this value from that formula only, 500 value. So we have set this one. We will be setting the compare values here only. We can also select in percentage, so I am taking the percentage values. So I am taking frequency as 20 kilohertz. So this will come out to be 5000, means 4999. Phase shifting is coming, as you can see on CRO. So this is the phase shifting method by master and slave. Other one we can use directly the compare values, different compare values, and select the phase shifting. Means if we select these EPWM is starting from 0 to 0.5, means the duty is 50%. So this thing will be generated by 50 duty from 0 to 50% of that cycle. And by selecting that EPWM2 with compare value A as 0.1 and compare value B as 0.6, we can generate this value from 10% duty to that 60% of that cycle. So here you can see that from 0 the EPWM1 is starting, and it's going up to 50% of that cycle, full cycle. And then EPWM2, the phase shift that we require, we can generate from this compare value, and then we can change this value according to our phase shift. So this EPWM2 is generating from 10% of that whole cycle, and it's going up to that 60% of that cycle. So the duty is 50, but phase shift here is 10% of that cycle. So I will be considering an example of dual active bridge converter to show that how phase shifting works. So this is single phase shifting of the dual active bridge converter. As we can see that here we have switches, 8 switches, total 8 switches. So S1 and S4 in single phase shift, S1 and S4 will get same pulses, and S2 and S3 will get complementary pulses of that S1 and S4. And S5 and S8 will get the pulses that is some phase shift with respect to that S1 and S2. As you can see here, these are the waveforms of S1 and S4. These, these are the waveform of S2 and S3. These are from S5 and S8. This is S6 and S7. So you can see that here is some phase shift between these two. Means the primary and secondary bridge have some delay. Means some phase shift. So I have provided this by a second method by only changing that compare values. So this is one example, and phase shifting is required to change that characteristic of that inductor current and inductor waveforms. So this is the single phase shift, and in extended phase shift, we can see that the characteristic of inductor current and inductor voltage have changed. So this is the extended phase shift. Here we can see that there is a phase delay, phase shift between internal primary switches and primary and secondary switches also. So this is the extended phase shift example. The other one is double phase shift example. So you can see that here there is a delay between primary switches and primary and secondary switches and secondary switches also. So this is the double phase shift example, and then we have that triple phase shift. Now you can see that in triple phase shift we are getting moreover a sinusoidal current waveform, but in that single phase shift we are not getting that thing. So in this will help us to accurately transfer that power from one side of means transformer to the other side. So that's the example of phase shifting. So now Sudarshan will.
Uh, Till now we have seen the EPWM with different phase shifts of different phase shifts also we have observed. Now we will see the peripheral with DAC. So so coming to DAC now, um, we have a direct DAC block in the MATLAB. You can observe here. So we are going to use F28370 DAC. So here how to what is the reference voltage of the DAC value? So this will be equal to the ADC reference value. So DAC voltage value will be equal to ADC reference voltage, which will be set by the which is set by already Texas Instruments. That will be equal to 3 volt. So here we are using 12 bit counter. So it will be having 3 volt. It will be equal to 2 power 12 minus 1. So it will be 3 volt will be given to 4095. So the maximum value we can give to DAC will be only 3 volt. That digital value will be equal to 4095. So whatever we give analog signal, it must be converted to digital. So that conversion can be done by adding a gain 4095 divided by 3. This is the gain value which we had to set before any analog signal we have given any ADC signal or sinusoidal signal or any DC or AC signal, that must be given to the gain of this value, and then we have to give connection to it. So we'll see, let's see now AC signal, like sinusoidal signal, how to give to DAC value. So first I'm taking a sine waveform. And as we know that we cannot give negative signal to the microcontroller, we have to give all the positive signals only. So we have to shift our sinusoidal signal above zero reference. So let's say we have now our sinusoidal signal was like 0 to 1. So this has to be shifted by adding one more we have to refer this is the reference ring. We have to shift this to the above 1 volt. So we can see here uh, this is -1 and this is 1. So we should make this at 0. So in order to make it 0, we have to add one DC count. That can be, then the signal will be, this reference 0 point will be shifted to 1 and this peak will be equal to 2 and this will be 0. So now the signal has been shifted above 0 reference, which can be given to the microcontroller. So we are giving now signal. How to add this reference? Uh, how to add this additional DC value in software? So let's first define the sign, then we'll go to how to add it. So I'm giving 50 as signal, and I'm giving sampling time 5e power minus 5. And now I have to shift the signal. So I'm so our sine signal is 1 amplitude. So we are adding one more 1 to make its reference value from 0 to 1. So whole signal will peak value will be 2 and reference value will be 1 and negative peak will be equal to 0. So we are setting the DAC channels. We have two DAC channels in our microcontroller. So here we are using DAC. We have DAC A, DAC B, DAC C. As I said earlier that this block is not dedicated to only 283790. We have different block channels also. So we have to use only either DAC A, DAC B for this model. So we are using DAC A now. So I am building it up. And output of the DAC will be output of DAC will be like this. You can see here we are getting the 50Hz signal and 2 volt peak. As I said, the signal of 1 amplitude has been shifted to 2. So this will be 2 and this will be 0 and reference will be 1. So peak value is 2 volt. Sorry, I forgot to add the gain. This will be 4095 divided by 3. Done. it has built up. Now let's see how to give this DAC A value to reference value. ADC. We are now going to see ADC peripheral. Here we can see ADC modules. You have different modules A, B, C, D, and input channels. We have different input channels. Based on availability of the pins, we are going to select the channels. So here, uh, see here we are using ADC resolution will be 12-bit and 16-bit. So 16, if you use 12-bit, we can use single under channel, where signal must be shifted to above zero reference. But if you use 16-bit channel differential input, then both negative and positive signals can be given. But here the disadvantage of 16-bit pins using is that for one signal generation, we have to use 2 pins. So whatever availability of the pins will be reduced by half. So based on your availability of the ADC pins, we have to use either 12-bit or 16-bit. So right now I'm using here 16-bit, and I'm using there are different numbers of SOC trigger numbers. You can start a conversions. We have here 0 to 15. This will be in round robin conversion, round robin rate of startup conversion, and we are giving 15-minute accuracy window, and we have different trigger sources. One can be software. Again, we have CPU timers and EPWM blocks. As I explained previously that in EPWM we can trigger an event. So using an EPWM block, we can trigger this event by having ADC EPWM 1A or 1B. I will show you block where how to show it, which event we can do. Here we are using event trigger. Here we have to enable either one module A or B. That means that module A pin and 1A pin will be using a triggering the ADC pawn channel, or 1B. It can be used either 1A or 1B, or you can have the EPROM interrupt also. So based on using this enable interruption, we can start the sampling startup conversion of the ADC. For time being, we are using software trigger. And sampling frequency will be keeping as 120 kilohertz. And input channel I am using here 2. Why 2? Because we have to see the input there. I am using here I am using JP4. I am using this JP4 jumper to sort the DAC 30 pin and 29 ADC into. It can be sorted here such a way that whatever DAC channel A has been whatever the DAC channel we are getting in A, which is 30 pin, we are showing to sort it. We are using this jumper pin to sort the 29 and 30. So whatever DAC A channel signal is getting, we are giving that input to the ADC into. And now I need to see this signal in the DAC B. So I have to use when the DAC, as I said, we are using already DAC A, we have to use DAC B, which is pin number 70. you can see the output of DAC B pin. Here, whatever in DAC A we have generated the sinusoidal, and that we have given to ADC into, and from ADC in again we are sensing it to DAC. So here we are getting the output. So already here the ADC reference voltage will be 3 volt, which will be converted into 4095, and that will be directly given to the DAC, which converts 4095 to 3 volt. So we have directly connected without any gains here. Now, see, now we have here simultaneous ADC blocks. Here we have A, B, C, D. So if I use channels here, ADC in A, if I use the same module with different input like ADC 1, or you can see let me take ADC in 3. And if I define same starter conversion trigger numbers 0, if I use this same number, then we are going to get an error. See here what they have defined here, that we have given same SOC trigger number. But if you want, but we have the access of simultaneous sampling times. So in order to access simultaneous things, we have given here ADC A block. So in order to have the same simultaneous SOC trigger, we have to use different channel, not from same channel. So I have used there A, so I have to use here B. So then you can see I'm using the same trigger number SOC 0. So then we can see it can be run. So for having, similarly we can have here simultaneously four things. So we have 4 channels, so we can have four ADC channels can be sampled simultaneously. So we can have A, B, C. So four from A one channel, B one channel, C one channel, one channel, D one channel. So 4 ADCs can be simultaneously sampled at the same time. Again, we have if we have above 4 channels, then we have to here we are having SOC trigger 0. So we have to give number SOC 1, and we have to wait. So if we have 4 ADC channels, now we will be having a delay of 16 nanoseconds here. So first this ADC channel will be sampled, then again after 16 nanoseconds this channel will be sampled. So there will be a difference in 16 nanoseconds delay in the sampling of A and B. So in 1 and 2. So now practically we have sensor signals where AC will be coming. So how to shift the signal practically? So AC signal will be here, we can see here. As I said earlier, that ADC reference value is 3 volt. So let's say our AC signal is having this is the AC signal which will be 50% up and 50% down. So we have divided this 3 volt into 2 halves, and so 1.5 and 1.5. So we are giving a voltage of 1.5 volt shift. So we are making this zero reference to 1.5 volt. So whatever AC signal you are going to give, it should be in the range of, this peak value must be one, here will be 3 volt, and this will be 0 volt. So that means that in general, we have to restrict our AC signal to only 1.5 volt itself. So we have to make our sensor output should be that AC signal should be only having a 1.5 volt itself. So then giving this 1.5 volt, DC source, we can shift our signal using DC and subtractor. Sorry, not subtractor, sorry. Adder. This is an adder. This circuit completely called as using op amp, we can add this two signals. We are having two signals here, we can add this, and this will be added, and this is an inverting amplifier. So here we can see that how will signal will be getting signal shifted. So here we already have, let's say this point is called VO1. So VO1 equal to minus, let's say this is RF, and this is R1, and this is R2. So minus RF by R1 into V in plus minus RF by R2 into 1.5 volt. So our signal, whatever we are going to get, will be shifted to like this. So it will be negative half. So to convert this again, this will be completely negative part. So to convert into positive part, we are adding one more converter, one more op amp amplifier, which is an inverting amplifier. This will be converting this whole negative signal to positive signal, and where whole signal will be coming in positive. Using this amplifier, we are going to get the signal like this. So this signal can be given to the ADC pin. So now my colleague will be telling you how to write a program in CCS Code Composer Studios.
Thank you, thank you. So hello everyone, I am Sudarshan Singh. I'll be introducing the CCS Code Composer Studio and how to write the code and all. So let's start. So I hope that everybody has successfully installed their CCS in their laptops or personal computer. So these are the steps for creating our new project. So first one is we'll be creating a new project, then we'll be adding libraries and header files. Then we'll be writing our code and build up the code and debug the code. So the thing is that there are two ways you can write the code. One is in the assembly language. Another one is by using the header files and writing in embedded C. So just for the convenience, so everybody can be a little bit interactive, we'll be using only the header files, and in the embedded C programming we'll be using. So our first step is to open the CCS software. You will be seeing this dialog box, and with the workspace they'll be defined. Just click launch on it. And then we'll have a second step. So this will be our second step. So in this, they will be asked our target and connections. So click on the 2837XD Delfino that we are using, and also the microcontroller name which you'll be using. And the connection will use this as a 100 V2 USB debug probe. So after clicking all this, we'll click on finish, and then we'll be we'll be able to see, like, third step would be to go into this sample. You'll see a main C file. In this, we'll be writing our code and everything. So, and the next step is to connect our hardware. We have to build up a file which will be connecting our hardware, and also all our code would be dumped in through that. So it is through by this target. We'll be going again to this sample. We'll be clicking on new, and we'll be clicking on this target configuration file. A dialog box will appear in which you have to write a file name. File name can be anything. The extension would be ccxml. Okay. So now next part would be to add some includes and all the header files which I talked about in my first slide. So in this we have to include certain device supports and all the common headers and all those things. Through that we will be able to access all the GPIOs and ADCs and all the things which has been shown in your MATLAB configs. So I'll write one of the code and show you how these things are being done. So let's open our Code Composer Studios. As you, so it will ask our workspace, which I showed in. So here you can see our workspace. Just click on launch here. So our objective of the programming in this, I've taken one example in which we'll be generating two EPWMs, which will have a phase shift between them about 180 degrees. So you can use this technique wherever is required. So let's create a new project, which is CCS project. As I showed there, you need to click on your target, which I have already done, and also the connections and everything. Just write a name. So we'll name it as sample 1, and then we'll click on finish. Now clicking on this, you'll be able to see your main C file. In this only we'll be writing our code. Now let's build our target configuration file. In this we'll name this as anything, but the extension should remain the same. So sample 1 target. So as you can see here, our target has been selected. So this is the microcontroller which we are working on, and it has been selected. Now the another thing that has to be done is including all the header files. Now we'll go on the properties. What we'll do is we'll include the option here, and then we'll be selecting few includes here. So you'll go to browse. You'll already have this Windows C in your C is where my Texas, all my folders of the Texas are there. So you click on TI, then you click on C2000, then you click on this, and you go into device support, and our name of our device is this 37XT. Now what you need to do is you need to include these things. Header, include, select this folder, and yes, it's been included. No need to, you need to select one more. You go to common. Now you include all these things. Include this folder. Now click on OK. Now these includes have been done. Now we need to define some predefined symbols. So these are for the CPUs that we'll be using. So what we are using is CPU 1. So for that, we'll write this. And let's write another name of our launchpad. Click on OK, then apply and close. Now what we need to do is we need to again add some header files, which will be specifically be doing for the GPIOs, EPWMs, ADCs, which were being discussed. So what you need to do is you need to go here on project and add files. So you go to common. You go to source, and then you can see these ADCs. So there are certain files that you need to add before you write a program and they can run. So these files are basically the registers, the name of the registers, and all those the bits that you can the play around with. Though they are present here. So let's click some of them which we need. So now click on open, and then you can copy the files here. Now you go to header, now you go to CMD, in this we'll be selecting our CPUs, so non-BIOS CPU. Okay. So for defining our global variables, so we need this file. So now our so whatever files that we need to add, we have done it. Now the objective which I said, I'll reiterate it. We need to generate a 5 kilohertz PWM signal with a 30% duty signal, and we'll be using it using the channel 2A and 3A while using a down mode counter. And and the thing is that here we need a phase shift, 180-degree phase shift between them. So I've already written a code. I'll explain a bit about it. So as you can see, the first line, what it says is that you need to include all the header files. This is for mentioning this. The other two lines is for declaring our functions. Now these functions, what they do is that first one is your GPIO select. And now in GPIO select, what you need to do is the like previously what it was said. Now you have a EPWM frequency as 100 megahertz. You can scale it down by using the clock div, and you can HSP clock div. I have scaled it down by division of 2 to each. So it will be around 25 megahertz. Now what you can do is if you go in, if you can select this TBCTL register, and inside that TBCTL register there is a bit named CTR mode. In this CTR mode, what you can do is you can select your mode, up mode, down mode, or up down mode. And now this line, what it tells is that it's defining a TBPRD. TBPRD was already been discussed. You can write down on the formula and everything. What we need is we need a period of 5 kilohertz. So depending on that, we'll have our TBPRD value. Now these values are for compare A. Now compare A, it will define it is defined for generating a duty. Now we need a 30% of duty, so it's a 0.3 into the TPBRD value. The next line, which is been which are here, as you can see highlighted portion, it's the action qualifier control register A. It is used when you need to switch on at the particular event. So 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 the how we are generating our duty is that we are generating a down counter whenever our compare value, whenever there is a zero, when it hits zero, we'll be setting it to low. And whenever it hits the compare value A, which has been mentioned as 0.3 into 5,000, 0.3 into the TPBRD value, it will set to high. So this is how you'll be generating our duty, our pulse. So my colleague discussed about the master slave configuration. Here what I have done is the same as master slave configuration. In this, what we need to do is that we need to define one as a master. So my EPWM2 is being defined as master through my phase shift equals to 0, and by providing the synco cell equals to 1. What it does is that whenever it hits the counter value equals to 0, it will provide a signal to its slave, and that slave would start from the TBPHS, the time period phase shift model. From time period phase shift, it will start from there. So the values actually has been changed whenever it provides synco cell output to the my slave. Now the same thing, now I've done my configuration for EPWM3 as slave. All the things are same, just there are two difference. What I'm doing is that I'm making it as a slave of the second one. So what I'm doing is as I'm enabling a phase enable equals to 1. It follows whatever the above one is following. And phase direction, it has been shown here, it equals to 0. It is only used when you want to use the up down mode, but we are not using the up down mode, only the down mode. So it is better to use it here, not to use. Now this innate system control, what it does is that it initializes all the watchdogs, all the peripherals and everything. It's more like a waking up my microcontroller to wake it up. So another two line, that GPIO select, this is that I'm calling my function, and it's a while and infinite while loop. So what it does that all the EPWM, it will continuously be generating. So it will not stop. If I don't have a while loop, it will stop just by generating one pulse. And now in this GPIO select, what I've done is that I need to, now these pins are we need to act them as an output pins. So it was being told in the previously that for making them as an output, you need to make sure they are that they are equals to 1. Okay, and they both are in the the mux 1. So 2A is my active, 3A is also active. So let's run it. So first what we need to do is we need to uh, debug this program. Now you can see in your console that it is all the files have been linked. The files are being successfully linking together. This is because we are adding all the correct header files. Now you can see it's a build finish. No, 38, 36. Now what you need to do is we need to debug this, click on this. Now when it's starting for the first time, whenever the program starts for the first time, it will pop up this dialog box, click on OK. And yes, it will be, there will be few pop-ups will show up. You just need to wait till they are run, till they complete their process. So this file has been is placed in the flash memory, not the RAM. We are not using the RAM right now. For if you want to use the RAM, then you need to again add one more header file, which will give you access to the RAM. So currently we are just using for flash only. Now let's click on run here. Mm. 38 and 38, 36. So as you can see here, we are having two, and they are being phase shifted by 180 degree, and they are duty of 0.3 and 5 kilohertz is the frequency of them. So that's it. So thank you everyone for attending. If you have any doubts or anything, you can please ask. Thank you all for just a kind audience for us. Thank you.
Hello, sir. Hello. Hello, sir. So I have a
Hello.
query, sir.
Hello.
So if I
Hello.
need to, yes, sir. If I need to monitor my ADC value in serial monitor,
Sorry,
then
sorry.
what would
Can
we
you
do in
please repeat it
MATLAB?
again? We are not able to hear you. Hello.
Hello, sir. If I need to monitor my ADC value in serial monitor, what would we do in MATLAB?
That you need to use, there is an option called monitor and tune. Just wait, give me, I'm showing, yes. See here you can see that there is a monitor and tune option also you have. So you have to use that option to monitor your ADC output. Actually, due to time constraint, we are not able to show that monitor and tune option also. Otherwise, we have planned to show it. But it's already 5:30. We're not able to show it here. But using this option, you can see the output of ADC in the scope itself.
Means there is any another block to watch the ADC output. Means for serial monitor.
Actually, we didn't explore much about more than that. Actually, we are able to monitor to the scope itself, so we have restricted till there itself. So we are still exploring a lot, but we are required time for that. Hello.
Yes, sir.
Uh, any other queries? Any queries from the participants? I think there is no more questions from the participants, so we can end our session.
Thank you, everyone. Thank you, Professor Susovon Samanta and Professor Indrajit Sarkar and our research scholars for this very informative session on CCS and interfacing with MATLAB of C2000 and the programming. So I hope it will benefit our research scholars for their projects. So thank you very much. Have a good day. Bye. And yeah, of course, tomorrow we'll join at 9:30. So see you at 9:30.